Hey, this is Sanyam Bhutani and you're listening to Chai Time Data Science, a podcast for data science enthusiasts where I interview practitioners, researchers, and Kagglers about their journey, experience, and talk all things about data science.
Hello and welcome to Chai with Research Heroes, CTDS.Show. In this episode, I interview Dr. Fatma Guney, who's a computer vision researcher. And as you can imagine, we talk all about computer vision, her research interests. And if you have been listening to the podcast, we talk about her approach to problems, broadly speaking. We also talk a lot about optical flow and self-driving cars. How are these two connected? If you're not familiar, we also talk about what is optical flow. Fatma also teaches a few courses based on computer vision, and we dive into her take on what should students focus on in this field and many great advices along the same lines. I hope you're as excited. I learned a lot. I learned a lot about optical flow, or broadly speaking, optical flow, unsupervised techniques, occlusions, and computer vision. Yes, all of these in one single interview. So if you share that excitement, on that note, without further ado, here's the interview with Dr. Fatma Guney. Please enjoy the show. Hi everyone, I'm honored to be talking to a computer vision researcher, Dr. Fatma Guney, on the show today. Dr. Fatma, thank you so much for joining me on the podcast.
Thank you for having me, Sanyam.
So I'm always excited to be talking to researchers. I don't get to talk to as many researchers on the podcast. Like always, I want to start the conversation by talking about your journey into academia. So if you could tell us, why did you decide to pick the traditional route of doing a bachelor's followed by master's followed by PhD and then postdoc?
Actually, I wasn't sure what to do in the beginning. I always had this question like, should I switch the industry? Should I start making real money at some point? Even after my PhD, I was interviewing with Google Zurich, but then Oxford site wanted me to decide earlier than Google. I just decided to do a postdoc. It's just how it worked, but I was equally close to both options, basically. It's not like I always wanted to be an academician at a university. It wasn't like that.
Do you personally, people tend to draw a line between academics and industries? Do you personally see any differences being in academics?
The line is quite blurred at the moment. Like, for me, it's just like my criteria is that I need to be able to do interesting research. And this is possible both at a university and at Google or at other companies, startups, etc. at this point. And we are very lucky to have this. By the way, I think it's a luxury. We have the luxury to choose, basically. We can
Definitely.
both make money and do good research.
The lab is just a PC, sometimes a big GPU machine for research.
Yeah. Let me turn off my mic.
Sure, no worries. So another thing about PhD that I picked from your website was you mentioned for your PhD students, the most important requirement is they should be highly motivated. Why, in your opinion, is this the top requirement? Any extended thoughts on that?
Did I say the most important? I mean, one of the most important, definitely, but I think I have a list. I think being motivated is definitely one of the first requirements, because it's as we talked before starting, it's a continuing learning process. You should be willing, you should be willing to learn all the time. Like, go learn if you don't know something. If you don't remember basics, you should go watch tutorials. And this is how you do things in research. I think being motivated is the most important thing. Also, another thing, we keep failing, right? We keep getting rejected. To be able to deal with this kind of thing, or the number of papers, even every day you see another paper working on something similar to what you do, to be able to deal with this kind of mental challenge, you need to be motivated. I think this is the only way.
Do you think motivation can also surpass the fact that many times experiments don't succeed, since you're literally answering unsolved questions, and most of us wouldn't have any idea how to navigate that?
Exactly. Yeah. You try 100 things. If you're lucky, one of them works. Partially works. Yeah, definitely. You should keep trying. You should keep going. Michael Black used to say that. I was in his lab during my PhD at Max Planck. He was listing this being resilient as the first thing that you should have as a researcher, because we all get rejected papers, right? This is like, to be able to deal with the feeling of rejection or imposter syndrome. I think all researchers have these kind of feelings. In order to deal with these challenging thoughts, you need to have the motivation to come back after a rejection or after a feeling of failure. Not fail, maybe you don't fail, or you just see yourself as a failure, right? It's important to be able to deal with these kind of feelings, I think, negative feelings.
One of the misconceptions I personally had was academia isn't as competitive as the industry, and later I realized, just by looking at the papers, which now I'm able to read some of them, is that there's so many papers coming out, and there's also this huge competition in academia as well, probably bigger than the industry.
Yeah, that's true. But I think compared to maybe 7 or 10 years ago, it's not as challenging, I think. It's more scattered at the moment. But still, most people choose to do both, right? Like they are
Yes.
affiliated with a big company and then they also teach, which is great. I think I really like that kind of settings. Yeah.
Okay. So you've dedicated yourself to very interesting research ideas. I want to start by talking about these. Can you share your research interests? And if I may, these are broadly motivated by self-driving cars. Can you share more about them?
Actually, I usually think of it as computer vision, but the main application is, yes, it has been autonomous driving because of my advisor. Andreas was one of the main creator of Kitty dataset. I used other datasets which are not autonomous driving datasets later in my PhD, but that's how I started, and mainly these are the problems that I'm interested in, yes.
So you put out, I think, if I may, again, I'm not familiar with the terminology, a survey paper in 2017 discussing the SOTA techniques on self-driving cars, autonomous driving broadly. What do you think is the state in 2020? What are the interesting challenges today?
You mean in general computer vision, or in self-driving cars, or perception of self-driving
Mix of
cars?
both. CV applied to autonomous.
I, I, I think it's a long topic. There were like multiple workshops at CVPR last week or a few weeks ago on this. For example, one thing that came up a lot was that the data that we cannot collect, the situations that we cannot have data for, like the accidents, rare cases, these kind of settings, we really don't know how to do it at the moment. And this came up a lot in the discussions. Both Raquel from Uber and Andreas, my advisor, they both talked about this a lot as the first or one of the biggest challenges that we need to handle.
Okay. And there's another topic that I found through your profile, which is 3D computer vision and tracking of actions. Can you share a bit more about these? What do these problems aim for, and the challenges there?
Yeah, sure. Basically, when I first started my PhD, I started working on one of the most traditional problems, stereo estimation. I was doing old school energy minimization, conditional random fields to solve disparity estimation or stereo estimation. This is how I got into the world of 3D. And then as a follow-up project, basically we weren't solving it like people did. We were also using semantic information to solve depth. We were one of the first people to use object information, like imagining how a car looks like and using that kind of information in the energy, forcing the random variables, which were superpixels in our case, to obey the rules defined by a 3D shape, which is displet. We called it displet, the shape of the car. And basically we were imagining how a car would look like and using that information in our formulation, solving the depth in a way that is informed by the semantics in the scene. And in our case, that was just the shape of the car. In a follow-up project, we extended to 3D reconstruction. We were learning the shapes of the cars as well as the houses on the street and using that information to make the reconstruction better. Because what happens is when you drive in Germany, you see these houses which are very similar to each other, but most of them are painted white. And if you have white surfaces, matching doesn't work. You don't get any interesting points that you can match between consecutive frames as we did in the reconstruction case. So we were just taking the mean shape, doing just PCA on the shapes in 3D, first detecting the objects and then doing a mean shape and using this mean shape as a cue, how a house should look like in the reconstruction to fill in the missing information. Because like left wall, you see in, for example, 60% of the houses, but you cannot reconstruct in this certain example because of reflection or whatever, like there is a tree occluding it, right? You cannot match. So we were using this mean shape information to make the reconstruction better or more complete in a sense, to have more points. That was our contribution. So this is how I started working on 3D. And then after publishing these 2 papers, I was halfway in my PhD and Andreas asked me what I want to do next. And I think we were at a point that we both know that my thesis is, I can write something, it's fine. And then there is one more project that we can do. And he wanted me to have more freedom, I guess, to take more freedom and choose what to do next. And then, we were part of Michael Black's lab at the time. And Michael Black he's an expert on optical flow. Everyone I know, all my friends were doing cool visualizations of optical flow, false coloring. So I wanted to work on flow towards the end of my PhD. That's how it went, basically. So was it the question? You asked about 3D, but I started telling
I did. It's definitely an answer to that. I'm curious, is this the reconstruction, is it based on camera based images, or do you have depth data as well?
We have depth data. It's called depth map fusion. Basically, we were using fisheye cameras in that project. You get 2 fisheye images from left and from time step t and t+1. You compute depth, and then you have all these depth mapped at consecutive time frames. You fuse them into the reconstruction, depth map fusion. That's why it's called fusion.
Okay, so you're also tracking the temporal features in this case for the fusion.
So that comes from motion, yes, but it's not exactly tracking. It's just thinking about 2 consecutive frames at one for computing the depth and then fusing them into the final reconstruction. It's not tracking in the sense that you have a consecutive linking in a window. Because I also worked on tracking later. They are similar, but it's different.
Okay, so if you can also elaborate on optical flow, what is that, and what does that address to broadly?
Optical flow is tracking. Optical flow is tracking of pixels one by one from one frame to another. You have 2 consecutive frames and you want to know for every pixel where they went from the first frame to the next frame. And this is why it's hard. It's a dense estimation task. You have to do it for every pixel on the image. Why are we interested in this? Because it tells us the motion of the pixels on the image. If we can get the general idea of what's going on in the video from this motion information, we can do a lot of interesting things. For example, people use optical flow to recognize actions. There are certain motion types that you see for an action class, like if it's basketball playing, right? Like the motion of the ball or the bouncing ball motion. All these things are very useful cues to recognize actions most of the time. Some actions you can just recognize from a single image, like the fridge, opening the fridge case. This is a famous example from Alyosha. He says, whenever the algorithm sees an image of fridge, it just says opening the fridge. There's no opening yet, but it just estimates opening the fridge. Yeah.
Okay. And if I were to rephrase that into a single tweet, can we call optical flow as semantic segmentation in videos? Is it roughly similar to that?
So I think it's definitely relevant. All these problems, okay, like depth estimation, semantic segmentation, optical flow, they're all relevant. They're all trying to explain similar things around the world around us, which is like the motion is affected by the semantics, right? Because there's an independently moving object creating the motion that you see on the image. But they're all looking at the same problem or same scene from different perspectives. That's why it helps if you solve even two of them together. Like if you do depth and semantics together, it works better. If you do flow and semantics together, it works better. But in the raw sense, if you define optical flow, there is nothing about semantics. It doesn't even consider the 3D world, right? If you consider 3D, it's called something else. It's called scene flow. So these problems have been studied independently, traditionally. Recently, people started thinking of them as a whole. Like, yeah, there are a lot of scene flow methods which uses instance information, like segmenting the cars and trying to explain their motion rigidly. These kind of works are number one on Kitty at the moment. There's definitely a benefit to think of them together, but in the definition, like traditional definition, they are just separate problems.
Okay. You
Definitely.
mentioned the Kitty dataset, and I think you might agree that eventually all research bleeds into products, different sort of products. Most of the self-driving car or computer vision related examples I see are on Kitty dataset or another similar dataset. I forget the name. Do you think? How do you think we'll make that jump to making it generalized better? Let's say to Indian streets, because KT is specific to another country and it may or may not work across another.
Definitely not with Kitty or any other dataset that we have at the moment. It won't work. It won't generalize. Like transfer learning is hard. And transfer learning at the level of challenges, not just appearances, right? I think it's a long overdue. Like we cannot solve it at the moment. It will take some time, I think. Kitty was good. Kitty started things in 2012. People, we couldn't evaluate, for example, stereo flow in such large scale until Kitty. There was only Middlebury, for example. Middlebury had 10 images or something. So Kitty created challenges that are very different from existing data sets. But now for deep learning, Kitty is very small, right? Like that's why we get another driving data set every other day. We have now BDD 100K, Argoverse, new scenes, all these interesting data sets that I cannot even download because they are so big. We keep buying discs to just have a look at it, you know, like, it's just so much data, but I think what is missing also the quality or variety in data. We had this big table in our survey comparing these data sets from different perspectives, like the variety, size, or the challenges they consider. We had these columns and we had like some checks for everything a data set achieves. Like each data set becomes a row in this huge data set table, in this huge data set table. So yeah, for example, we are working on video object tracking or detection, and we don't have labeled datasets, labeled video datasets for that problem other than Emoti and Kitty at the moment. I thought that BDD 100K had these labels, but no. They only label, for example, one frame in a video, which is not useful at all if you want to do something temporal, right? Yeah, it's a bit disappointing that datasets cannot catch up with the things that we want to do.
Yes, and as you mentioned, eventually we want to put these into the real world, and what we want is example or edge cases where an unfortunate accident is happening, which almost is rare to capture.
But
And
I think they are two different things, right? In one case, you can collect data. In the other case, you cannot, right? We will never have enough data for the variety of traffic accidents that one might face in the traffic. These are two different problems. One is problem of data, which you can go collect, label by putting enough money into it, or for like labeled force into it. And the other is definitely something that we need to take care of without having the data, probably. Maybe with simulation, people are betting on simulation. I was in this autonomous driving workshop. Both Raquel and Andreas, they were mentioning this flexible language that we can use to create scenarios, realistic looking scenarios, so that we can simulate these events, like various events, accidents, whatever can happen, and then learn from them. I'm not sure if this is the way to go, but this is one of the solutions that is being tried at the moment. There was a recent paper from Uber.
Do you think games can be an answer to that, since games are getting more and more realistic in terms of physics? Gamers call it physics.
Yes, that's what I meant by synthetic world, right? Like when people talk about this flexible language, they talk about creating realistic looking simulations, I think. I don't know, I haven't read the paper yet, but I think that's what they mean. I mean, we all know the problem of transfer learning, right? We had this discussion in the workshop that we organized, Optical Flow workshop in 2018, because Optical Flow, we cannot collect data. We definitely depend on synthetic if we are going to do supervised learning. So Thomas Brooks's group created flying chairs for FlowNet in 2015. Then they developed it into Scene FlowNet, Flying Things, Monka, whatever, right? And then there was the data playing for benchmarks, this data set. I think for Flow, if we want to do supervised, that's the only way to make it work. But then again, I think it's not answered clearly if this will work in any situation in real world, right? Also, the gap is closing. Unsupervised method is getting closer and closer to supervised methods in Flow. Like we have unsupervised Flow paper from Google, which came out in April, I think, or sometime in April. It's an ECCV submission. So they reported similar results or better results than FlowNet 2, which is one of the number one benchmarks from a couple of years ago, right? Like, I think the gap is closing.
This also allows me to segue into talking about your recent research work. The paper is titled for the audience, Unsupervised Learning of Multi-Frame Optical Flow with Occlusion. If you want to look it up, or you can find the link in the show notes.
Yeah.
Can you tell us more about the findings? And I try to ask this question to break down how does research happen. So if you could also break down, how did you think of this idea and how did you approach the problem?
Yeah, we are not the first to do optical flow unsupervised. It has been studied by a couple of papers at least before us. Basically, the way it works is you have two images usually, and two consecutive images. You estimate the flow from one to another. You've warped the second frame according to the estimated flow and compare it to the first one. Warping is basically moving every pixel according to the flow that you estimated, imagining the other image according to your estimation. This is what warping is. So what you should expect is exactly the same as the other image, right? If you estimate optical flow correctly, if your optical flow is like ground truth accurate, then you should get exactly the same other image. But this doesn't happen because of occlusions, where we have occlusions, for example, my hand is moving and then occluding my face. So you get these problems in the motion boundaries, which is called ghosting effect. So you have a problem where the hand leaves like this, the position that was occupied by the hand on the first frame, and then on the next image you have the place where the hand moves to, right? Like you have this double effect, which cannot be handled.
Which, if anyone from the audience is watching this video on YouTube, you can literally see it happen with the virtual background.
Yeah, exactly. Occlusions happen because things move, and we have this problem. So previous methods did certain things for occlusion. For example, there was a method which just ignored occlusions by computing forward-backward flow. In forward-backward flow, you basically compute flow from the first image to the second, then from the second to the first. And if you do this trip from first to the two and second to the first, you should reach the same location approximately. There's a threshold. And if you cannot, this means that you cannot estimate flow reliably in either this way or this way, right? And then you can use this information to detect occlusions. It's called forward-backward consistency check. It's also used in stereo. this way you can detect occlusions and ignore them in the loss function because they are misleading. You cannot match if a pixel is occluded if you have 2 frames. So what we did differently was that, can you reason about these occlusions? This is the first question that we asked. Can you find where the occlusions happen unsupervised? Second question that we asked was, can you make use of this information to have something, some information about the pixel all the time? So to make this happen, we basically looked at more than 2 frames. We had a future frame and a past frame. We computed 2 flow, one into the future, one into the past. And the basic principle is that if a pixel is occluded in the past, look into the future. If a pixel is occluded in the future, look into the past. If it's visible in both, which is what happens most of the time, then use information from both sides. Just fuse them by weighing them equally. That's what we did. And really interesting part is that how to weigh them is also learned, estimated by the network. So network tells which direction to look, like how confident you should be about future or how confident you should be about past is also learned by the network with this occlusion mask. Yeah.
Okay.
That was the main idea, and we were the first to do multi-frame and occlusion learning together in a framework. We got really good results, even by training on a dataset that we created with some synthetic images from Flickr. We were just downsampling one image and use it as a foreground and move it a little. Like you get occlusions, right? Whenever you move something. So yeah, that's how we trained it. And even training on this simple data set to learn occlusion relationships in this temporal window, we could get very reasonable results both on Sintel and Kitty. When we fine-tune it unsupervised again, not using labels at all, we got very reasonable occlusions which look like ground truth, both on Sintel and Kitty. I mean, yeah, this was number 1 in 2018 and even in 2019 for a while. And then this Google paper came up and they did very extensive experiments like which data terms to use, which smoothness to use on which data set, how to do occlusions, etc. They didn't compare to the multi-frame setting where you learn the occlusions, but with the 2-frame case, they experimented with everything you can think of, like the pre-training, batch size, whatever you can think of, and they got better results. Basically, they are the state of the art right now without using multiple frames and occlusion learning. But then again, I want to add, there was a CVPR oral, mask flow net, which learns occlusions in the supervised setting. So they didn't supervise occlusions, but they supervised flow and learn the occlusions from the supervision of the flow. And the way they do it is that they estimate this occlusion mask theta, which learns to filter out occlusions in the feature map, not on the image, but in the feature map, which is quite impressive. And then there is this very good idea, I think, mu trade-off turn, which helps to learn large occlusions, for example. And their experiments are also quite impressive, I think. The way the paper is presented is quite cool. But one thing they don't do is they say that they are the first to learn occlusions, which is not true. We are the first to learn occlusions. I'm a bit mad at reviewers when they don't catch these things, basically.
It's also, I think, due to the huge outflow, research is easy to miss. There's such immense amount of papers coming out almost every day.
Not really. Optical flow community is not that large. We all know each other, I think. But it's easy to miss because they do supervised and our method was unsupervised. So again, supervised for flow, unsupervised for occlusions, but still.
Noted.
Yeah.
I also use talking about a particular project to break down how a researcher like you would approach the problem. So if you could, using this as an example or otherwise, share how after, let's say you decide to work on an idea, how do you iterate upon that? How do you build the experiments, or what does your pipeline look like?
So with unsupervised flow idea, Joel, I think, PhD student that we worked together on this paper, he was already working on it. I was writing my thesis. Then I finished my thesis. I had a couple of months in between. So we started working on it together. We worked together before. We already knew each other. Our style of working was similar anyway. But so what we did is we took the state-of-the-art method from NVIDIA, which is PwCnet, state-of-the-art for any type supervised flow. And then we tried training it unsupervised by using the photometric loss that I told you about. But we got very bad results. The motion boundaries, everything was really bad. And then we thought, what could cause this? I mean, we all knew that occlusions were problematic, but then we thought, how can we handle occlusions? Okay, we can do something about occlusions. We can try to estimate occlusions. But let's say we estimate the occlusions, how can we make use of it? Can we incorporate it in the photometric loss? If we do, can we make use of information from both directions, feature paths? Basically, it was an idea which developed based on the errors of the current model. Also, we tried several things. It's not just like this idea worked out of the box. When I left, we first extended PwCnet to multi-frame. This was very complicated because if you know PwCnet, there are multiple layers in it. There are like 6 layers. So you have a deep learning model which does loops. It's always dangerous. Like there is the danger of mixing up the indices and everything. You do warping, then you upsample it. There are a lot of options, like do you learn upsampling? Do you do just bilinear interpolation? So many choices to try. And we also got help, by the way. There was another student in Italy, Matteo or Fabio, I cannot remember. I'm sorry. He was using PwCnet for stereo estimation anyway, and he had good results on Kitty. So he was very kind to share his implementation with us. We were comparing if we are making any mistakes, because at the time PwCnet model was not available, right? And NVIDIA didn't share the code yet. It was just an archive paper submission in 2017. It's submitted to CVPR, but they don't share the code until it is published usually. So we were trying to implement it without a reference implementation. So like the code on stereo helped us to compare our solution to do sanity check, see if there was a mistake. Yeah, that's how we proceeded with the model. Then for the loss functions, we were checking the results, state of the art very carefully. What kind of photometric losses? For example, you cannot just use L2 loss. It doesn't work. You need to know the tricks. People use robust functions like generalized Charbonnier and all these things. You need to go look at other people's code. It's not gonna work if you just use the first thing that comes to your mind. There is years of experience, like the Secrets of Optical Flow paper, which got the Test of Time award, right? This CVPR. So that's where Michael and De Ching introduced the generalized Charbonnier loss, I think. And since then, it's one of the best loss functions for optical flow, for doing robust estimation of optical flow. So basically, we were building on top of other people's code. We took the model from NVIDIA, we took the loss function from a paper from 7 years ago or whatever. So yeah, you need to know the literature very well. That's the trick. And still it didn't work. When I left, it was still not working. Joel worked on it for a couple of months more, and the deadline was in March. And he told me one day, we just have the best results, beat the state of the art. I was like, what did you change? And he told me, nothing and a lot of things. You know, there is a bug in your code. You have to debug it very well. You have to keep trying until it works, if you trust your idea, I guess.
One of my favorite quotes is machine learning models, when they fail, they don't give you a stack trace or an error trace. They just fail silently.
Yeah, exactly. You need to know all these small tricks, especially in vision. I'm not proud of it, but that's how the problems are, or how the field is. You should look at other people's messy codes sometimes. You should read a lot of papers, tricks. You should know the tricks. Yeah.
You mentioned the idea didn't work for a while, and this is also one of my favorite questions, which is what do you do when an idea doesn't work and you've tried yours?
I think most of the time, like 90% of the time, idea didn't work because I had a bug in the code. You cannot give up. You should always doubt your code. There's always some index, something that you think that it does the right thing, but it doesn't. some people recommend unit tests. I have unit tests at a larger level. I test modules like general ideas, small ideas, but still, I mean, you can think of it like parts of an idea. If I have an assumption, if I don't know if it's going to work out of the box, I try to test it visually. I have a lot of like debugging visualizations, step-by-step intermediate visualizations. Also, Andreas used to tell me to sort the results according to error metric. See where you expect to improve. If you improve there, fine. If not, what is wrong? Like go back and see what assumption that you made is wrong. This kind of debugging, like debugging, but at a higher level. For example, to debug stereo, there are other things. To debug flow, there are other things. It depends on the problem a lot. That's why it takes time to get accustomed to the problem. Once you know the problem, you can keep publishing fast, but until you become familiar with the problem, it takes a while, I think.
Are you still Team PyTorch? I know you had released a framework in Torch. Are you Team PyTorch or Team TensorFlow right now?
No, I started with Lua. My first paper in 2016 was in Lua. I was writing dilated convolutions myself in Lua with the help of some guys from Torch. Francisco, actually, he was quite nice to me. Anyway, I remember deriving things on the paper and implementing it. Those days were quite different. I feel old when I think about it. But then this project was also in Lua because I think we had some of the models implemented in Lua. So I said that we used PWCnet, but this was not the case since the beginning. So we were in the same lab with the guy who developed SpyNet. So we started with SpyNet, but SpyNet was very hard to optimize because they train levels separately, which is not ideal. We switched to PWCnet not after a while, basically, after some experimenting. And this model, SpyNet, was implemented in Lua. I knew Lua, and Joel started learning Lua, so we implemented in Lua. But I think we also have an implementation in PyTorch. I'm not sure if it is released, but Joel was working on it at some point. Now I'm using PyTorch fully, yeah.
For the audience, Lua is a framework. If you're not aware, there are frameworks outside of TensorFlow and PyTorch as well, if you'd like to look it up.
There was no PyTorch before, okay? There was only Torch and TensorFlow, and I chose Torch.
Fair enough. So this is again one of my favorite questions. I just have one 2080 Ti, which also I'm fortunate enough to. This one, as you can see, is for ray tracing purposes, as you can tell by the RGB. How do you think an independent researcher who's interested in computer vision, maybe someone who doesn't have extensive hardware, can contribute to problems? What interesting areas do you think they can contribute to?
I mean, you definitely need to compute, but you probably don't need 16 V100s to make contribution. Yeah, I don't think people should get discouraged by this too much. Yeah, experimenting helps a lot. And in all of these papers, I had access to maybe 30, 40 GPUs at MPI.
Not a lot.
But I don't think that's a requirement. I don't have that kind of setting at the moment, and I can still do research. I didn't have that kind of setting at Oxford either. I had 2-3 GPUs at most at once. And this is already okay to develop ideas, right? You need more GPUs only when you want to cross-validate things or when you want to do some hyperparameter search. Yes. And most of these things are kind of robust now, right? You can look at the paper before you and set the same learning rate or whatever. It's not the main factor, I think, affecting the results. The main factor is realizing what is missing, looking at the existing methods, knowing the literature very well, and knowing their weaknesses, seeing what is missing, running these things, right? Like take their results, see what is wrong, and build on top of it. Don't try to be a hero and do the object detection from scratch. This will never work, right? Like you have to know at least faster RCN, and you have to read the detector on code, and then maybe you can build on top of it. I know that it's very hard to publish in an object detection paper because it's dominated by Facebook, whatever. But there are still smart things, smart ideas that you can come up with and get better results. Also, you don't have to get better results in all aspects, right? You can handle a certain thing. For example, you can find a certain weakness. For example, this occlusion case, must flow net. Okay, they're number one on benchmarks, but still, they knew that occlusions didn't work, so they proposed a specific solution for that. I think knowing the literature and analyzing the results of the best methods that are out there is the key.
Okay. So I'll also take a step back to look at the broader picture, which is for someone who's starting to learn. You also teach a few courses at university. I'd like to ask you, what do you think is a mistake that we new machine learning students tend to make while pursuing projects or learning?
I think thinking of the field as very big, I think most of my students think that they are too late to the game. That's not true. We are just starting.
Even in 2020?
Yeah, I think so. I think we keep doing the same things right now. We all just evolve around the same ideas. When you start reading maybe 2 or 3 problems at the same time, you will see that we go around the same ideas. Like someone discovers robust whatever for one problem, another person goes try it for another problem. I mean, I don't want to simplify it like that, but it's not as much as people might think in the beginning. When you start learning, in the end, you're like, you look at a paper for 15 minutes and you know what's going on.
Yeah.
It's not that different after a certain point. It's important to get this big picture, and for that you need to read a lot. You need to watch a lot of talks and go to conferences, talk to people, learn. But then after a certain point, it almost becomes repetitive. When I see an interesting idea, I get excited. I mean, I get excited very easily anyway, but most of the time the methods just build on each other, which is, I think, the right thing to do, right? I'm not judging that it's like not novel enough, whatever. I'm just saying that we work together towards similar goals.
I would say, if I may say so, thanks to the pandemics, you mentioned about meeting people at the conferences. Everything is virtual now, and earlier I wouldn't have even dreamed of attending ICLR or CVPR, and now you have to. You can, if you want, just jump on a Zoom call. So that's also, to me, even though I feel very intimidated in front of researchers because it's another language that they speak, but it's more accessible to outsiders, so to speak, in my opinion.
Yeah, but it's missing a very important component, I think. It's missing the fact that you can just go chat someone, get introduced to your machine learning heroes, as you say. This doesn't happen now, right? Like last ECCV, I got to meet Jitendra Malik. All these kind of things happen only if you're in a friendly environment. Your friend introduces you to someone and that person introduces you to another person. This doesn't happen on Zoom. You don't talk to people that you don't know. Which is,
if I can argue, like someone who tries to step outside of their comfort zone, they can try and engage with them if they are available, assuming
it's very hard.
Session.
Would you go say hi to Jitendra Malik? I wouldn't.
I wouldn't dare to, but if I really want to, I might give it a shot.
I would never, but I appreciate, I mean, I admire your courage, I guess.
Okay.
I mean, I get excited even seeing Andreas. I know him for how many years now? I saw him giving a talk. I was asking a question, and then he said, "Oh, Fatma is a student of mine." I'm like, "Oh no, he's mentioning my name."
I wear a Apple Watch which warns you when your pulse shoots up high, and throughout these interviews, even today, I'm sure I have had the notification once or twice. I share that enthusiasm with you.
Thank you.
So
Yeah.
coming back to learning, many people tend to learn online, and I'd be curious to know your thoughts on how do you think the boundaries are blurred between MOOCs and university courses. But otherwise, how do you suggest someone gets the most out of a machine learning course?
I think, yeah, there's still a difference between taking the course, doing all the assignments, talking to other students doing the assignments, solving things together. This is definitely still important, like in class discussions, right? everyone can go watch all the videos about object detection, but no one tells them which method is better than the other, or comments on funny things, or say that this is why it's working. That's what this method did on top of the other method. This contrasting thing, comparing things. That's what I try to do in my course. I think that's what should become like we have access to all these great materials. We can go watch the talks, read the papers, but the missing bit is that critical thinking, right? Like arguing what is good about this paper, or what can be improved in this paper, what works, what should we learn from this paper. These kind of things, what I'm trying to achieve with my students when we discuss things. I ask them questions like what they really like towards the end of the course is that I was asking them to review papers, to write like what is good about this paper and what is bad about this paper.
You have a few prerequisites. I was going through the course website. You have prerequisites to read before lectures as well, I think.
Yeah, I copied this format from Raquel. She had a similar course in Toronto in 2016, I think. It was very hard for the students, by the way. They spent all their weekends reading 2 papers and reviewing them. It was the first time they did it. But I think they were glad in the end, because the big picture thing that I mentioned, they could build it, by reading all these state-of-the-art papers 1 week after on different problems. They got this big picture, I think, roughly. Maybe not, they didn't understand everything in the paper, but they could skim a paper first and then read in detail, find what is missing or find what is working. And, they could compare their reviews to in-class discussions. Then we had people presenting every week 2 papers, 2 people presenting 2 papers, and then we had some discussions about the paper, so they could see, what they did right, or if they could find a certain thing. I made it even more item-like thing towards the end. I was preparing, so towards the end we didn't have presenters. I had to come up with discussion points. So I made it like a list of questions about the paper, like specific questions. What is this? How does it help? Where does it help? Why does it work? Why it doesn't work? Can you comment on this table? Why is this row in this table is better than the other row? Like very specific questions, but important questions for understanding the thing that is proposed in the paper. Most of the students really like this, because they said that they usually don't know what to focus on in a paper, like which table is more important, or what is the message of this table. These kind of things really help them to ask the right questions, I think.
And I think going back to your answer, now I realize that this guidance might be difficult to achieve through a MOOC or an online course.
Achieve what? Sorry, say it again.
This sort of guidance, broadly speaking, would be slightly more difficult to achieve through a MOOC, where you have this feedback.
Because most people have this mental block, right? When we read a paper, we always assume that this paper knows everything and solves the problem perfectly. But that's not the case, right? If you look at from the reviewer point of view, there are a lot of things that you can criticize, or that even if you don't have to be critical, right? You can also say that, what if they did this? What if instead of this experiment, could they do this kind of thinking I'm trying to build? Yeah.
So this is my final question. I ask a lot of stupid questions to very smart people like you, and I always get different answers. This is my favorite question, which is, what would be your best advice to future researchers and future machine learning students who are just starting out?
You mean what would I recommend?
Any best advice, broadly speaking, to someone who's starting their journey?
Starting vision. To read a lot, I guess. To read a lot and to try to code, not to be scared, not to get discouraged by the fact that there are a lot of people working on these now. There are a lot of smart people working on these problems. But I think you can still find a place to yourself if you put the effort, if you're determined, if you keep, staying excited, if you keep putting the effort.
If you remain motivated.
Exactly, you can become part of the community. Yeah, I think don't get discouraged. That would be my first message. Then the second message, really work hard. Really, like read everything, not everything, but everything from good conferences. Code a lot. This would be my advice, I guess.
if I may highlight, you mentioned read a lot, but please don't forget to code. Like you said, what happened with me was I had this mental block that I don't think I can read papers. And once I was able to, I would go there on streaks just reading papers. Implementing stuff is also important. Try to replicate what you're reading. Do code, please. That's also important.
Luckily, most of the people share the code for their papers, so you can just go find the paper for the code. But reading other people's code is also a very good exercise, right? Seeing that how these people implement things efficiently helps me a lot to improve my coding skills. For example, I would think, would I implement it this way, or would I just write a for loop? I usually do the for loop because it's safe. But there's always a better answer, right? There's always a better structuring the files that you create, folders, even the structure of your code is something that you can improve all the time.
That's where the tricks lie, like you mentioned.
Yeah. Like I love these codes from research engineers at Facebook, like Detectron. It's pro, right? You can read that code, and it's like a course on coding.
Certainly. Okay, before Fatma, we end the call, if you can just mention the platforms where you're most active so the audience can connect with you if they like to.
Sure, I'm active on Twitter, which is my public persona. I'm also active on Instagram, but please don't add me. It's more private. Yeah, Twitter probably, or my email.
Okay, I'll have both of them in the show notes as well. Fatma, thank you so much for joining me on the podcast and for sharing all of these amazing advice.
Thank you. It was a pleasure talking to you.
Thank you so much for listening to this episode. If you enjoyed the show, please be sure to give it a review or feel free to shoot me a message. You can find all of the social media links in the description. If you like the show, please subscribe and tune in each week to Chai Time Data Science.